Okay, protein structure. This lecture is divided into 3 parts and there'll be 3 videos accompanying them. That's what we'll be covering in broad outline. Look at proteins in the diet, look at the microstructure of proteins, and look at proteins in food structure with some examples. So proteins in the diet. Here's a little exercise for you to do. If you're watching the video, press pause and examine the list. Which of these foods are high, medium or low protein? So I'm assuming you're pressing pause now. Okay, we're back. Unsurprisingly, tuna is the highest and bananas the lowest. It's worth remembering, of course, that fruit and veg contain a lot of water. Although they're often good sources of protein, it's relatively small amounts in absolute terms. Westerners tend to get much of their protein from milk and dairy sources. This is marked contrary to Asia, where only minor components in the diet from milk from proteins or dairy sources. In fact, many of the population are lactose intolerant, though that is changing with more people becoming lactose intolerant in the West and people becoming a bit more lactose tolerant in Asia. Worldwide, cereals are the most important source of proteins, especially in Africa. Although reasonably high in protein, such a diet may lack specific amino acids, and we'll talk about these in terms of limited amino acids and essential amino acids in a short while. So back to nutrition. Not all protein sources are equal. Nutritionally, amino acids fall into 2 categories. Non-essential, which means that we can synthesize them in our own biochemistry from non-protein sources or possibly from other proteins and amino acids. Essential amino acids, abbreviated EAAs, which refers to amino acids we must get from food. Note that tyrosine and cysteine can be synthesized, assuming we have enough of the essential amino acids phenylalanine and methionine respectively. When an amino acid is not provided in adequate amounts in the diet, protein synthesis is limited to the rate at which that essential amino acid is available. These essential amino acids are then referred to as limiting amino acids. The first limiting amino acid is the essential amino acid that first becomes deficient in the diet. In many cases, it is often lysine. Although not necessarily for the module, if you want more background on human amino acid requirements, click on this article. It's got quite a lot of good information in there. Okay, structure of proteins. All proteins are composed of 20 standard amino acids, chains of 20 amino acids arranged in a huge number of different ways. These are primary alpha amino acids and are said to be because they have a hydrogen atom, an amino group, a carboxylic acid group substituted on the same carbon atom. They also have a substituent group designated R here, which is a group that differs between the amino acids. R is just a general term. There's obviously no element R. We'll see some examples of that shortly. Amino acids, so as we've said, are 4 groups arranged tetrahedrally around the central alpha amino acid, which is that one. However, so that's 109 degrees 28 minutes bond angle. However, the individual bond angles will be influenced by the nature of the individual groups, especially the R groups. So in glycine here, the R group is another hydrogen. That's the simplest amino acid. Whereas in alanine, the R group is a methyl, a CH3 group. That's the next simplest amino acid, if you will. So apart from glycine, all amino acids can exist in 2 distinct 3-dimensional forms. These are non-superimposable mirror images forms and are referred to as enantiomers, and there's the examples there for alanine. We'll talk about what D and L means in a moment. So what do we mean by non-superimposable mirror images? Your hands are a good example. They are mirror images which cannot be superimposed on top of you, as is shown by the image here. Here's a picture of the world's oldest iPad. Have a think about that. Which parts are chiral? That's just say I have non-superimposable mirror images. Yes, it's earbuds which are chiral because your ears are chiral. In general chemistry term, chirality arises when we have 4 dissimilar atoms or groups bonded to the same carbon atom. As noted, amino acids are a good example of this, apart from glycine, which only has 3 different groups. Right, okay, so why is chirality important? Virtually all biological molecules show chirality, and it's responsible for much of the richness and specificity of biological chemistry. For example, the enzymes that hydrolyze proteins and amino acids rely on very specific binding in 3 dimensions. That's true of all enzymes, of course. If the key doesn't fit in the lock, the enzyme won't work and the reaction it catalyzes will not take place. So how can we distinguish these enantiomers, these DNLs we talked about a bit earlier on? We use a polarimeter. This is a scientific device used to measure the angle of rotation caused by passing polarized light through an optically active substance. So polarized light, as we can see in this image here, is light which only vibrates in one plane compared to over here, compared to light, which is normal light, which vibrates in many planes. It's been passed through a slit in this case, often a diffraction grating. So it's turned into light which vibrates in one plane, in this case up and down. It's passed through a polarimeter, and depending on the optical activity of the substance which is dissolved in a liquid in a polarimeter, the plane of the plane polarized light will be rotated to a certain amount, either to the left or to the right, which we can detect using an analyzer. If you click on this image here, there is more information on polarimeters. Okay, so how does this allow us to do this? Solutions of 2 different enantiomers of optical active substances, that is to say substances which will rotate the plane of plane polarized light, like D and L-alanine here, rotate the plane of plane polarized light in opposite directions. You may see 2 different ways of describing this. Plus or D for dextrorotatory, that is rotation to the right. Minus or L for levorotatory, that is rotation to the left. So, light passes through a polarizing filter and continues a straight line through air. When it passes through a solution of water, light still continues in a straight line. Water is not chiral, though of course many chiral substances may be dissolved in it. However, when we dissolve equal molar solutions of opposite enantiomers of a chiral subspecies, they rotate the plane of plane polarized light in opposite directions by equal amounts. The numbers used here are arbitrary, they're just an example. If we increase the strength of both solutions, the amount of deflection is increased by equal amounts in opposite directions. So this is a way of estimating the concentration of optically active substances. You would do a calibration line and you take your unknown and calculate from its optical rotation what its concentration was. Think about what happens when a solution containing equal amounts of A and B. Pause the video and have a think about this. Okay, as we can see, the 2 optical rotations cancel each other out. The solutions are said to be racemates or a racemic mixture. Most amino acids are in life in the L form. There are some examples of D amino acids, but many of these are very toxic indeed. Okay, that's all for now. We'll be back for part 2 shortly.